Okay. Let's start then. Okay, so welcome to the course. This is the first lecture, and the scope of this lecture is to give a friendly and not necessarily very mathematical introduction to persistent homology. Okay, so first, what's topological data analysis and what's persistent homology? Okay, so topological data analysis aims to detect and characterize topological features and to analyze in general the shape and structure of, let's say, high-dimensional data. Persistent homology is perhaps the most common, most used tool in topological data analysis. And despite being a relatively recent tool from the, let's say, past couple of decades, 15, 20 years, persistent homology has already become ubiquitous with several different applications ranging from characterizing molecular structures, including proteins, to study neural networks, to studying and analyzing single cell data. Sorry, people online, could you mute yourself? Thank you. To study oncological data and much more. This is just to mention a couple of the several different applications. The plan for today is, as I mentioned, to arrive to give a definition and to reach an understanding of what persistent homology does, how it works, and what can tell us. To do that, we need to introduce some of the theoretical tools that we need to define first homology and then its persistent counterpart. So we start by defining the concept of simplices and simplicial complexes. Once we have that, we start talking about homology and back to numbers. We'll give the idea and definitions, and we'll give some examples, some really not really a computation, but some example. And then we'll start finally to talk about how you can obtain a sequence of simplicial complexes of topological spaces from data, and from this information how you can define and compute persistent homology, and what, again, persistent homology can tell us about the data. Next time, Oliver will tell us some more technical variations, some generalization of the basic concept of persistent homology, and on the third lecture we'll see some software and computation, some more involved computations that you can do using software. Oh, and speaking on that, I should say that if you received the invitation and looked at the PDF, there's a link there to download data to follow the computations on your own laptop on the third lecture. Please, even if you have already downloaded stuff, perhaps go back on the saved link after the weekend, because I might change something. Sorry about that. Please wait just another couple of days before downloading. All right, so let's start by going towards the first part, introducing this concept again of simplices and simplicial complexes. Actually, sorry, I think I'll get rid of my mask, if you don't mind, because I'm already out of breath. All right, so intuitively, a n-dimensional simplex is a triangle in dimension n. Now how can you see the slides? Right, so I should be sharing my screen. So if you click on one of my accounts and you set that as a main screen, you should be able to see it. Is anyone else having problems with seeing the slides? I should be sharing my screen. Are people seeing them?
Cara here has your screen.
Cara, you're online and you see my screen from your laptop. Yes. All right, so perfect. So it's one of the windows, so if you click on the right one, it should be, there might be I'm from my iPad, I'm sharing my iPad, so look for my name with an iPad or one of the three one of my 3 accounts. Okay. All right, so again, intuitively, an n-dimensional simplex is just the generalization of the concept of a triangle in dimension n. Throughout this presentation, we go back and forth from a geometric interpretation of simplices, again, as the generalization in arbitrary dimension of the concept of triangles and their abstract representation. Geometrically, an n-dimensional simplex is going to be the convex hull of n plus 1 points. As a standard example, we have the standard n simplex in the standard n-dimensional simplex, and this is just going to be the set of points in Rn plus 1. Is it a question or sorry? In Rn plus 1, such that the following condition is respected. The sum of the coordinates x0 plus xn is equal to 1, and all the coordinates are positive. Just to have a visual representation of one example, in dimension 2, the 2 simplex is just the convex hull of the 3 generating vectors of the Euclidean space in dimension 3, thus a triangle, what everybody knows as a triangle. Abstractly, the abstract counterpart of geometric simplices is just, we see simplices as subsets of n plus 1 elements, so an n simplex is a subset of n plus 1 elements of a universal set. What do I mean here? I mean that abstractly, from a combinatorial point of view, I'm just going to think about a simplex as being identified by the vertices of, its geometric counterpart. So again, the standard to simplex, from an abstract point of view, is going to be the set of E0, E1, and E2, where again, the EIs are just the 3 elements of the standard basis of R3. Any questions so far? Good. And N, so the cardinality of the set defining the simplex minus 1 is the dimension of the simplex, okay? Again, dimension 2 to simplex, 3 points, the usual triangle. This is just a schematic for what an n-dimensional simplex is for n equal for dimension 0 to 3. In dimension 0, an abstract simplex, an abstract 0 simplex is just going to be the set of a unique element, or geometrically a point. In dimension 1, a 1 simplex is going to be determined as a set of 2 elements, or geometrically as a segment with 2 vertices. Dimension 2 we already know, we have 3 points and a triangle. In dimension 3 we have 4 points and a solid tetrahedron. Any questions so far? So again, as you can appreciate from this schematic, in each dimension we have, let me repeat myself, the generalization in that given dimension of the concept of a triangle. All right. Now, the first part of this lecture is going to be just a bunch of definitions. We are going to need all these definitions to define homology and thus persistent homology. Please bear with me, and again, don't hesitate to ask me questions if there's anything that's unclear. I kind of don't know where to look at. If I look at the computer and I look at yourself, so I mean, just try to be loud if I'm not paying attention to people online or people here. All right. So another concept we have. Yeah.
One question. What does it have to be a triangle? Can it be square or something?
It's not a dumb question at all. So different people can give you different answers to that. I think the easy answer that I want to give to you now is that with this definition, everything works fine from a computational combinatorial algebraic point of view. I hope that answer your question. I mean, again, several possible answers. I think this would be the one that would satisfy. This is the answer that would satisfy myself the
His
most.
question was why not a square? He asked why not a square.
Yeah. So, for example, maybe another good answer would be that in this way you have a very nice relation between the number of points you need to define a simplex and what is the dimension, right? So, thank you, Heather. In this way, we maintain the fact that with n if I want an object that's n-dimensional, I need n plus 1 points to define it. So again, 2-dimensional, a triangle, and so on. Otherwise, how would you scale to 3 dimensions, for example, the concept of a square? In a way that this nice relationship between dimension, what we want the dimension to mean, and the cardinality. Right? Good. Thank you for your question. All right. So we need to define the concept of a phase, of a simplex, and again, I'm going to go back and forth from combinatorics and geometric interpretation. From a combinatoric point of view, a phase of a simplex sigma is a simplex tau sharing all the vertices with sigma. So a subset of the set representing sigma. In the picture, you can see a geometric representation of what a phase is. So we start from a 2 simplex sigma, and we have its 1-dimensional phases given by its edges, and these would be then the edge, the 1 simplex V0 V1, the 1 simplex V1 V2, and the 1 simplex V0 V2, and then we have the 0-dimensional faces of sigma, and these are also the 0-dimensional faces of the corresponding 1 simplices, and these are given by the vertices. Now, there is a little bit of confusion in notation here, because often when people talk about faces of a simplex, they just refer to subsets, faces of dimension equal to the dimension of the simplex minus 1. Okay? So, in general, a phase of a simplex is a subset or a subsimplex. In practice, when people talk about phases, they mean phases of dimension 1 minus 1. So, in this case, the phases of sigma would be only the 1-dimensional edges. All right. We are now finally ready to define the concept of a simplicial complex. Intuitively, a simplicial complex is just an object built by gluing together simplices. Okay, so said in the other way around, simplices and dimensional simplices are going to be the building blocks for our spaces, and our spaces are going to be simplicial complexes made up by simplices. This in the slide is just an example of a possible simplicial complex. More formally, we have a way to formalize this intuitive definition of a simplicial complex being objects built by gluing simplices. Indeed, we have a combinatorial definition of a simplicial complex as follows. So, given a set V0 to Vn, a set of vertices, a simplicial complex K is a collection of subsets of V, so a collection of subsets of vertices, such that the following two conditions hold. First, the simplicial complex needs to contain all the vertices, so all the subsets made up by a single vertex. Second, if I have a simplex in my simplicial complex, then all its faces need to be part of the simplicial complex as well. Now, I don't want you to think too much about this latter definition. It's a technical definition that's needed to make all the algebraic machinery will need to compute homology work. Following this definition, if this is in the figure is the geometric representation of our simplicial complex K, its combinatorial counterpart would be the following set, the following collection of subsets. So we have all the vertices, V0, V1, V2, and V3. Then from the figure, I see that I have filled-in triangle, and this is going to be the simplex V0, V1, V2. And I know that since I have a triangle, I need to have all of its faces, so I have V0, V1, one edge, V1, V2, V0, V2, and then finally I have this ladder edge, so V2, V3, and that should be it. Okay? So a simplicial complex is geometrically something that looks like this, combinatorically is a collection of simplices with these two conditions holding. Any questions so far? All right. Let's start by giving some example of simplicial complexes. So, trivially, each simplex is a simplicial complex. It is built by, gluing together a unique simplex. And if you think about a simplex as having all its faces in it, then the second condition holds as well. Less trivial example: all the simple graphs or networks, as you prefer to call them, are simplicial complexes. In particular, this is worth saying, simplicial complexes in which made up by simplices of dimension 0 and dimension 1. If you're into computer graphics, any triangulated surface can be thought as a simplicial complex. So, if you imagine a triangulated sphere, that's a nice example of a simplicial complex. Now, a natural question. Go ahead.
So a simple graph is a simple complex, but what about hypergraphs and sort of things like that?
That's a great question. So an hypergraph is not going in general to have the second condition respected, right?
The subsimplices, are they called?
Exactly. So if you have an hyperedge, let's say there's nothing in the definition of an hypergraph guaranteeing that you have all the. So that's a great question. Actually, you can think about hypergraphs as a wild generalization of simplicial complexes, like a little less regular. So simplicial complexes being, if you want, hypergraphs well behaved. Okay?
Thank you.
Great. Now, in the case of graphs, you don't have this thing, right? Because graphs are hypergraphs with only binary relationships. So if you have an edge, you have also the vertices, right? So the second condition is maintained trivially, if you want. All right. Now, you might ask at this point, our scope, is to define some algebraic way to analyze the shape of spaces. Is it enough to think about simplicial complexes? In other words, by considering only simplicial complexes, am I considering all the possible spaces, whatever that means, And the answer is kind of yes, meaning that, again, I'm not going to say a precise statement, but there is a theorem telling you that any space if it is regular enough, and I don't want to say what I mean by that, but any space, if it is regular enough, if it is nice looking enough, can be approximated. And again, I don't want to say what I mean here, but the intuitive idea is enough, can be approximated as a simplicial complex. Any space we might be interested in studying likely is going to be regular enough under this definition, so we can approximate it as a simplicial complex. Okay? All right. Oh, just came to my mind. I should have perhaps repeated the question from the audience here. You probably understood that from my answer, but the question was, what about hypergraphs? Are hypergraphs simplicial complexes? And the answer was not, because they don't respect the second condition, and blah, blah, blah. And then you should have heard the remaining part of the discussion. I'll try to remember doing that from now on. Okay, we are done with the first part. We are ready to start talking about simplicial homology. Okay? Homology or simplicial homology is, naively speaking, intuitively speaking, an algebraic theory whose aim is to detect and count topological feature of spaces. What do we mean by topological feature of spaces? We mean roughly finding and counting holes and higher dimensional holes in spaces. Okay? Now, everything I'm saying can be, precisely defined in algebraic terms. That's not what we are going to do today. And at the end of this lecture, I'm going to give you references for those of you that want, to understand the algebra behind it. But this is going to be hidden throughout this lecture. Okay, so. But ask me questions if you have any. Now, again, for the purpose of these talks, we are really not going to look into high-dimensional holes. We are going to think about zero-dimensional features and one-dimensional holes and two-dimensional holes, or if you want, voids. Okay? Now, before I give you the definition, I just wanted to give you some examples. So, just to set the expectations right and just to agree on what we should expect homology to be able to count. If you consider a topological space, a space like this one, this is the surface of a donut or a torus. We want homology to recognize the sorry, I see someone is not able to see the screen. I don't know what to do about that. I'm sorry. I'm logged in with 3 accounts, so just try and click on each one of them, and eventually you should be able to put my screen put the share screen as your main one. Anyways, we want homology to be able to detect and recognize the intuitive idea that everybody has, that the torus should have two-dimensional holes, right? One being the one defined by this curve here, so the hole of the donut, and then the other one being the hole defined by the fact that this is the surface of a donut. There's nothing filled in. Okay? So we would like homology to tell us that this has two one-dimensional holes. Similarly, we would like homology to recognize that a cylinder has a unique one-dimensional hole. Again, this one, or the one, if you want, defined by the following curve. Similarly, if we talk about graphs or networks, we want homology to tell us that I have one pole roughly for every cycle in the graph. And similarly, if I'm talking about a two-sphere, two-dimensional sphere, so the surface of a ball, I want homology to detect that this has no one-dimensional poles, but has a unique two-dimensional hole or void. I hope that intuitively you agree with me that these previous statements are true. Okay? So we want to define an algebraic theory that tells us this kind of stuff. All right, again, I need to go forward with a bunch of definitions. Okay? The first definition I'm going to need is the concept of the boundary of a K-simplex. K-simplex sigma. Here you can see it defined combinatorially, defined in using its abstract definition, so as a set of k plus 1 points, p naught to be k. The boundary of sigma is defined as the formal alternating sum of its faces. And again, here by faces, I mean faces of dimension 1 less than sigma. Now let's try to understand what I meant by this definition. So by formal sum, is there some question? Sorry, Oliver, can you mute? There's someone unmuted. Unless it was a question, in that case, please. All right. Anyways, by formal sum, I mean a formal sum is just a way to indicate an algebraic structure. Like, I mean, there's no really other better way to say that. Is a formal sum. Alternating means that I'm considering plus or minus signs on the faces, and in this way, I want to indicate the face of sigma obtained by missing the ith vertex. Okay, let's see it with an example. Make these. Let me make this smaller very quickly. All right, and let's see what is the boundary of this simplex sigma. The boundary, following the definition, is going to be the alternate sum of its one-dimensional faces. The first one that I want to take is defined by the index 0, so this is going to be minus 1 to the 0 of the simplex obtained by missing the point p naught, so this is the edge b1, b2, and this is just a plus, so I'm going to remove it. Then minus, because I have minus 1 to the 1, b naught, b2, plus v naught, plus, yes, v naught, v1. Oh, yes, thank you. Yes, go ahead. Is there a question?
Yes.
Go ahead, please ask.
Yeah, your definition of the simplicial homology, can you come again?
So I haven't given the definition. Okay, I just said that intuitively we want simplicial homology to be an algebraic theory that tells us how many holes of a given dimension are there in a simplicial complex. I haven't given a definition yet.
Okay.
Okay?
Yeah, thank you.
And to be fair, I'm going to give a simplified definition. Okay, I'm not going to give the full algebraic definition, but hopefully that will be enough to have an understanding. And I promise I'm going to give you enough references to have the full picture, full algebraic picture. I have a question from the audience and a question from here. Let me reply to the audience one first.
What does addition mean? Like, so over here, let's take the case of a graph, right?
Yes.
And when you say a node, what does addition or subtraction of a node mean?
So that's a great question that I'm not going to answer in full generality. From the next slide, so sorry, I should repeat the question. From the audience, have been asked what is the meaning of summing or subtracting simplices, okay? Now, the meaning, maybe the best question is this one. The meaning is to be able to add an algebraic structure to the set of simplices and make them a vector space or a module. For us, since, as I'm going to tell you in the next slide, we're going to use Z2 coefficients, so for us the multiplicity of a simplex is going to be either 0 or 1, a formal sum is exactly the same thing as a set. So taking the formal sum of two 1 simplices means considering the union as a set of these two 1 simplices. In its full generality, that's not true anymore. It just means thinking about the set of simplices as either a vector space or a module.
So is a multi-set sort of allowed? So if you say like a union, and assuming A union A is still just A, right? Or is it like a superset of union? No multi-set.
For simplicial complex is not.
Yes. So
There's other complex.
I mean, when I'm talking about the union, I mean so let me say that again. So you don't have a simplex union itself because I told you we are only using 0, 1 coefficients. Okay, so if I take twice of the same thing, that's 0. If, on the other hand, I was in an algebraic setting with non-Z2 coefficients, but for example with integer coefficients, then taking twice the same simplex couldn't be translated as taking a set anymore. It would be translated as, an algebraic operation in an algebraic structure. Again, either a vector space or a module. Question from, yes, please, maybe Maria?
Hi. I was wondering if you could give us an informal or intuitive definition for what a boundary is.
Yes, so I was about to finish here. If you give me a second, I'll let the other people ask their questions, and then when I finish with this computation, you'll have an intuitive. I promise you'll have an intuitive idea. Yes, Logan?
Yes, can you hear me?
Yes.
If you go up to the previous slide,
Yes.
I didn't hear what you said about the simple graph. How many holes does the simple graph have?
So it depends on the graph. In this figure here, 1.
Yep.
Now that's not exactly true, but you can think the following: a simple graph has as many holes as cycles. Then it's not exactly that. Okay. Okay.
Okay, thank you.
All right. Then I have Adewale.
You've answered my question.
Yes.
You've answered my question.
All right. Perfect. Then let's answer Maria once by finishing the computation. Okay. So combinatorially, this is the boundary, a formal sum of 1 simplices. This is the boundary of my 2 simplex sigma. Geometrically, this is just even by P0, P1. I'm keeping coefficients now, just, to maintain B1, B2, B1, B2 first. Minus B0, B2, so I'm doing something without explaining, okay, but hopefully it will make sense. Plus B2, B0, plus the edge B0, B1. Or if you want, by looking at my triangle, its boundary is B1, I didn't want to do that, I want to do this, B1, B2, then minus B0, B2, so B2, B0, then B0, B1. So it's boundary, exactly. Okay, it's an algebraic way to interpret what the geometric boundary is. And hopefully by looking at me tracing the boundary on the physical object, on the geometric object, you see why I need coefficients and the alternate, to trace the boundary. Then, that said, since again we are going to work with 0, 1 coefficients, plus or minuses for us are the same thing, but I wanted to keep them in the boundary definition because it gives a nice intuitive idea. It tells us that we are actually doing something meaningful from a geometric point of view. Okay, we are just trying to translate algebraically what the geometry is telling us. Okay, that's the theme of all algebraic topology. Okay, find an algebraic interpretation of things that you want to be true. Okay. All right, we are almost there. Okay, we have another couple of definitions, and then we can understand what homology is. First definition I need is a K-chain. Now, given a simplicial complex K, for example, the one shown here in the picture, a K-chain is a formal sum of K simplices, or in other words, C can be written as, again, a formal sum of simplices with a coefficient. Now, for us, again, this coefficient is going to be in Z2, so AI is equal to either 0 or 1. So again, a K-chain in this simplified scenario is just a set of simplices. Let me give you an example. If this is our simplicial complex, for example, this thing here is a chain, okay? And this can be algebraically written as the formal sum representing it, so E1 plus E4 plus E2 plus E6. Okay, so formal sum or set of one simplices. This is, of course, a one chain. Okay, and again, here I'm writing things in arbitrary dimension k, but for us, really, k is going to be either 0, 1, or 2, and really is going to be most times 1. Okay, in all of the examples, in all of the computations, it's going to be 1. In most of the computations, it's going to be 1. Okay. Any question here? Is clear what a chain is? Great. All right. Now that we know what a chain is, we can define a cycle, a K-cycle. So a K-cycle is going to be a K-chain with 0 boundary. So a K-chain such that if I compute its boundary, this boundary is 0. Let's give some example. And again, we are going to have this theme of geometric thing and algebraic interpretation, combinatorial interpretation. In this simplicial complex, a cycle is, for example, this thing here that we're going to call C1 algebraic given by E1 plus E3 plus E2, or C2 given by E3 plus E4 plus E5, or geometrically this thing here. Okay? I hope that intuitively you believe me that the boundary of these cycles is 0, but let's check it algebraically for one of them. Okay? For the other one, the computation is going to be similar. So let's compute the boundary of C1. Now in this computation, I'm not going to take care of coefficients, okay, or plus or minus of signs, because for us, plus and minus are the same thing, and if I have two of the same thing, then that's 0. So let's compute the boundary of C1. This is, I forgot to tell you, we defined the boundary of a simplex. From this definition, we can define the boundary of a chain as if the chain is a sum of simplices, then the boundary of a chain is the sum of the boundary of the simplices. Okay? So to compute the boundary of C1, this is the boundary of E1 plus E3 plus E2, and this is equal to the boundary of E1 plus the boundary of E2 plus the boundary of E3. And this is equal, now of course I cancel the name of the vertices. This is equal to the boundary of V0 is, of E1 is V0 plus V1. The boundary of E2 is V0 plus V2. And the boundary of E3 is V2 plus V1. So I have 2V0 plus 2V1 plus 2V2, and so this is 0, because they all cancel. Forgive me here, I said I wasn't taking into account coefficients and signs. If I had, and if I had been careful and kept signs in my computations, they would have cancelled. Okay, so I would have had V0 minus V0, V1 minus V1, and V2 minus V2. We said we don't care because we are in Z coefficients, and this makes things easier. But it would have worked even by doing things carefully. Okay, with, for example, integer coefficients. All right. And again, geometrically, we have something that's closed and something that's closed has no boundary. Okay? A circle has no boundary. An interval has a boundary. The circle doesn't. Okay? And that's exactly what the algebra is saying, is telling us. Last definition, a K-boundary is, again, a K-cycle whose the boundary of a K plus 1 chain. Okay? In this example, we had our cycle C1, C1 we said is a one chain, which is also a one cycle and is also a one boundary. Why? Because I'm not going to do the computation, but C1 is the boundary of the phase F. Okay? If you compute the boundary of F, you will see that that's exactly E1 plus E2 plus E3. Right?
Hello.
Yes. Go ahead.
Yeah, so your definitions, can you take it a little slow, and you can make the definitions 2 times so that we can really understand what you're trying to say. You're too fast in the definition.
I'm sorry, of course, okay. I repeat everything. All right, so.
No, yeah, I'm asking for the definition of the K boundary.
Oh, the K boundary.
Just come again.
Okay, so
yes.
A K boundary, let's put K equal 1. Okay, so a one boundary is a one a one chain, so a set of one simplices, which is the boundary of a k plus 1, so a two chain. Okay? In this case, we have C1, this cycle here. We already know that this is this chain here. We already know that this is a cycle, but it doesn't really matter. The point is that in this context, C1, this violet thing, is the boundary of the face F, and so is a boundary. Because in K, in my simplicial complex, I have a two simplex whose boundary is exactly this chain C1. Does it help?
Okay. Okay.
All right.
Sorry, can I ask?
Yeah, of course.
In chain,
Mm-hmm.
do the simplices have to be connected
No.
somehow, or could you have a situation where they're
No,
Right, okay.
they don't. Great question, actually. Yes, all my examples were connected, but you definitely don't.
Cheers.
Thank you for the question. Okay. All right. We are really ready now to have this, give this sort of definition of simplicial homology. I'm also aware of time, and you might be tired. Should we take a 5 minutes break, perhaps, and then I'll give the definition of simplicial homology? Should we reconvene at maybe it's now 52? Should we do even 3-4 minutes? Should we do 56? Just to take. You're welcome to, if you have questions, you're welcome to put them in the chat. I'll bring some tea, but I stay here, so. Sorry, Logan, if you're there, I can answer you now. Yes, it was a very bad choice of notation. So K, capital K is the simplex, so the space we are considering, simplicial complex, so the space we're considering. Lowercase k would be the dimension of the simplices we're considering. So here in
That makes sense.
all right,
That's what
so
it seems like.
yeah, and if you want, and now I don't want to do that because it's going to be ugly, but yes, dimension. You're welcome. Hi.
Small question.
Yes.
When you were, I think a few slides ago, you were drawing there's an arrow on the edges. Is this oriented? Is it a ordinate set, or is it just a set sort of thing?
If you are working with Z coefficients, not. If you are working with Z coefficients, yes.
Okay.
Okay. that, again, that's all these lines, all the coefficients and everything are needed, including, this ordering of sequences, are needed to make the algebraic machinery work when you are not using that coefficients. Like natural choice could be integer coefficients, okay? Or real coefficients. So you would work with set of sets, you would work with algebraic structure. Spaces, so yes, but not in our case. If you're interested in the algebra behind it, I give you free available material at the end of the lecture. There's going to be a slide with references. If you're interested in applications, we can work with that.
Of course, I'm just trying to connect and make the definitions we work with, trying to understand them.
So one way to have an idea of why you need this orientation is by looking at the boundary. Okay, you see, this is the boundary is V0, V1, V1, V2, V2, V0. So is and V2, V0 is minus V0. Okay, that's the minus there. Okay, so because you do that for the to fix the boundary. That's really the trick. Okay, then what you have in general is just a transition. Okay. It would be, too long and technical to give the full definition, and also since this is supposed to be now applied topology thing for applications that definition somewhere. Is there a question? I see someone with their hands. No, that was for your old question, I guess. Anyways, if someone has questions, just ask. Oh, it's already 57. Let me have another. Let me drink some tea and then we start again. All right. Okay. So, can you still hear me? I will assume you can. We are ready to define simplicial homology. Not quite. Okay. I need another couple of very short definitions. Now, we talked about k-cycles. We can consider, given a simplicial complex k, the set of all its k-cycles. Okay? And we call it zk. Similarly, we can consider the set of all its k boundaries for each dimension k. Again, for us, let's just think about one-dimensional cycles and one-dimensional boundaries, just to have a picture in mind. Okay, and the picture is going to be the same as the examples I gave. Given the set of cycles and the set of boundaries, and now I'm going to do a little bit of handshaking, we can define the kth, or for us, first homology group, or homology set in our case, of the simplicial complex K, the quotient of cycles over boundaries. Now, what do I mean by that? There's an algebraic definition for that. What I mean here is that I want to consider the set of all the cycles up to an equivalence relation given by the boundaries. So, this means that HK, the kth homology of K, is made up by all the K cycles where I count K cycles mod boundary. That means that 2K cycles are the same for me, exactly the same, if they differ by a boundary. What do I mean by that? Let me give you an example, okay, and hopefully that will give you enough intuition to kind of, have an idea of what I mean. Let's consider my old friend C2, this cycle here, okay, and let's consider now this new cycle I haven't considered before, and let's call it C3. And remember, I had another cycle already considered, and this was C1, okay? I'm not going to draw it, just remember, okay? It was, let me draw it and then cancel this one, okay? This will be C1. Now, you can appreciate from the figure, and you can check it algebraically, that C3 can be interpreted as C1 plus C2. Okay. Let's try to write this down. Okay, I have that C2 is equal to C2 is equal to E3 plus E4 plus E5. C1 it was E1 plus E2 plus E3. So their sum is this thing here. If you look closely, you see that I'm counting E3 twice, so they cancel. They cancel up. I'm working with the coefficient, and this is exactly C3. E1 plus C2 plus C5 plus C4. We knew that C1 was a boundary, and graphically you can see that the orange cycle C3 is kind of my green cycle C2 plus a boundary, plus something that's filled in, okay, plus a cycle that's filled in by a triangle, okay. In this, under this definition, if we look at H1, so the first homology, so the number of one cycles mod this equivalence relation, this one is going to be a set made up by a single cycle that can be represented by the cycle C2. So this is, it's a little bit a stretch, okay, it's not exactly correct what I'm saying, but you can think about H1 in this context as being the set given by C2. Or better, the set of all the cycles there, of which I'm taking C2 as a representative. Indeed, you would agree with me that the picture I have there is something with a unique one-dimensional hole, okay? This hole here, okay? Now, since we are getting rid of all the algebraic structure by looking at the coefficients, it makes sense only to talk about the cardinality of these homology groups, and these are going to be called the Betti numbers. I said at the beginning that we are really only going to look at dimensions 0, 1, and 2. You will have to believe me on that. I just want to tell you that the Betti number 0, so the cardinality of the zero-dimensional homology group of a simplicial complex, is equal to the number of connected components. So zero homology is a way to tell you of how many separate pieces a space is made up by. Similarly, the first Betti number, or the cardinality of the H1, is equal, as we wanted, to the number of one-dimensional holes, and this is the number of one-dimensional holes is thus given by cycles mod this boundary equivalence relation. And the H2 similarly is going to be equal, the cardinality of the H2, so Betti number 2 is going to be equal to the number of two-dimensional holes or voids. For our small, simple, simplicial complex here, we would have that Betty number 0 is going to be 1. I have a unique piece. Everything is attached to each other, so one connected component. Betty number 1 is going to be 1. We only have one hole. And Betty number 2 is going to be 0. I don't have anything really two-dimensional. I don't have enough two-dimensional structure here. I only have a triangle, not enough two-dimensional structure to enclose a void. Any questions so far? I know I'm not being, 100% precise. Everything I said has a very precise, very formal algebraic interpretation and definition, but I hope I was able to. So the scope would be for me now to give you enough intuition of what's happening and an idea of the algebra behind it, in such a way that you can work with it, and if you want to know more from the mathematical point of view, you can by looking at the references I'll give you. Any question? Okay, now we are done with the, just to finish, that's the same example that I gave at the beginning. If you perhaps I'm not going to repeat myself here, but you can interpret all of these spaces, or better, you can approximate all of these spaces as simplicial complexes, and if you apply the definition I gave you and you perform the computations, you'll see that what we wanted is respected. So for this space here we have Betty number 0 equal 1, Betty number 1 equal 2, and this is perhaps not super intuitive, but the Betty number 2 is going to be equal to 1. Here we are going to have, I'm going to use B from now on for Betty numbers. Betty number 0 equal 1, one component, Betty 1 equal 0, and Betty 2 equal 1. Kind of as we expected. Okay, again, of course, I didn't show you that. You have to believe me, but I hope you do. All right, last example, just to show you something that's actually not connected, because that's something we are going to deal with in a minute when we pass from homology to persistent homology. This is, if you consider these two cycles as a unique simplicial complex, this is an example in which we have B0 equal to, I have two separate pieces, okay? And B1 here is equal to 2 as well, because I have two independent, if you want, poles, okay? 1 and 2, okay? Any question here? All right, now, natural question at this point would be, okay, but our aim was to detect topological features and characterize the shape of data. We have only been talking about, combinatorial spaces, blocks, spaces made up by blocks that should resemble triangles. Okay, what does it have to do with spaces? So, with the data. So, what persistent homology does is define an algorithmic way to pass from data. So you start from data, whatever that means, to a sequence of spaces, a sequence of shapes, and given this sequence of spaces, it computes their homology, thus it characterizes their topological features. Now, let me say a few more words on that. So, for the purpose of this lecture, data for us is going to mean a point cloud, okay? So this means some finite number, finitely many points in some Euclidean space, in some Rn, perhaps. Just for now, we can think about R3. Okay? And the way, in its more simple situation, its more simple definition, what persistent homology does is construct from a point cloud a sequence of spaces that should, in a way that should resemble the intuitive idea of growing balls of increasing radius around the points in my point cloud. So I'm starting from a point cloud. I want to find a way to create a sequence of topological spaces in a way that resembles these, enlarging points to be balls to create stuff that looks like that. Okay? This is called the filtration of topological spaces. At each step in this filtration, I want to compute homology, and then the topological fingerprint of my initial point cloud is going to be the sequence of homology of the homology features of the Betti numbers I computed. Is the pipeline idea clear, or is there any question? All right, so let's try to give a few more details. Now, we've been talking about simplicial homology, okay? So we don't want to construct topological spaces given a point cloud. We want to construct simplicial complexes. And again, I already said that, but the topological fingerprint is then going to be given by computing homology groups of all the simplicial complexes in this sequence. So this schematic here in the figure is supposed to give, a more formal schematic of the pipeline. Okay, we start from points, we construct simplicial complexes, a sequence of simplicial complexes, a nested sequence of simplicial complexes. So the simplicial complex is one contained into the other, as shown here and as suggested by picture. And at each step, I compute the homology, the Betti numbers. So, in this very small example, if what's shown here is the sequence of simplicial complexes, the fingerprint of this point cloud, this set of points, would be the following one. So I start by having Betti number equal to 6. I have 6 separate points. I have no holes of dimension 1 and no holes of dimension 2. B2 is going to be 0 throughout this example. Okay, so let's forget about it for a second. Here I added in the filtration a bunch of simplices, so I have B not equal to, still no hole. So B1 is equal to 0. I added the two simplex here, okay, but nothing changed at the level of homology. I still have 2 connected components and still no hole. Finally here, I added a bunch of more simplices, and finally I have a unique connected component, and also I have one hole, this one. Now this is, a made-up filtration. There's nothing really, meaningful about the way I decided to draw the simplices. It was just to give you a nicer schematic of what's going to happen. Okay. Now, let me say that given, I'm only going to talk about point clouds, okay? But you can start from several different kind of data. And then, given different kind of data, or even given point clouds, there are several different ways of constructing filtration of simplicial complexes from it. What I'm going to tell you about is the simplest possible filtration, and the filtration that's supposed to give you a good approximation of this idea in a way that's combinatorially efficient. There are other better approximation of this, growing ball thing, but the filtration I'm using is the best from the computational point of view, and it's the one that's implemented by most of the implemented softwares, and the one implemented by the software I'm going to present to you on our 3rd lecture. Okay?
Can you say a question?
Oh, yes, please, go ahead.
plain version.
In the chat. Okay.
Can you see it? Otherwise, I can repeat it.
What is why is B1 equal not for the third image? 1, 2, 3. Because I have no one-dimensional hole, right? I have one cycle. This one. This is a great question. Thank you. I should have pointed out. I have one cycle, but this cycle is also a boundary, right? So it doesn't count. It gets cancelled out. I'm aware I haven't given you the exact definition of what taking this quotient is. But for the same reason why here I had only really C2 as a cycle, because everything else was either a boundary or was differing from C2 by a boundary, for the same reason here I have one cycle. I have this cycle, but this cycle is covered up by the boundary, so it doesn't define a hole, so it's not counted. It gets sent to 0 by the quotient. It gets annihilated by taking the quotient of cycles over boundaries. Does it answer your question?
Is it in a way because the triangle is filled?
Yes, exactly. Yes, of course. Yes.
Surface.
Yes. Thank you. Sorry, I thought it was. I should have said that. I thought it was evident from the figure, but yes, exactly, because it's the boundary of, because it's filled in. There's the triangle, so it is the boundary of the triangle. If I didn't have this triangle, then I would have had B1 equal 1, and B1 equal 2 here. Okay.
But sorry, which is the difference between the filled triangles and the empty ones?
The empty one is defined by a chain who is a cycle who is not a boundary.
Okay.
Because it's not there's no two simplex for which that is the boundary. If it's filled, then it is a chain. It is a cycle because it has no boundary, but it is the boundary of a two simplex in the simplicial complex. And so when I'm taking homology as the set of all the cycles mod boundary, it goes to 0. It's 0. It counts as nothing. For the same reason as in this image, the orange cycle and the green cycle are exactly the same thing in homology because they differ by a boundary. Similarly, the purple cycle is 0 because it is a boundary, it's the boundary of the triangle. And so I have only one homology here that can be seen as being generated by, for example, the green cycle. Okay? I understand, so like giving everything makes sense only if you give the proper algebraic definition, but that would require an entire course, okay? So these are all, very pertinent, very natural questions, and it's very good that you have them, and it's natural to have them because I have been imprecise. I would encourage you to read a little bit of the references that I'm going to give you, and I promise that if you read and follow the algebra, that everything makes 100% sense. But I'm shaking hands a little bit here, okay? All right. So I was about to tell you the filtration that's usually implemented in applications and that we are going to use today and on our third lecture. This is known as the Vittori-Slip filtration, and this is just a way to tell you how to compute from a set of points a sequence of simplicial complexes dependent on a time parameter t. Okay, so it tells you at each time t which simplices to add in your simplicial complexes to get in your simplicial complexes to get topological space at that time. The filtration works by telling you that at time t the points let's call them Vj1 to Vjm, form a simplex if and only if the pairwise Euclidean distance between any pair of vertices here, so Vj I1, Vj I2, is less than T. Okay? So as long as a pair of segments has the pair of vertices, sorry, has distance less than T, I add an edge between them. If I have 3 points whose pairwise distances are less than 3, I add a triangle between them, and so on. Okay? We'll see an example. Okay? Now, again, let me just repeat the pipeline. We start from points, we construct simplicial complexes. These simplicial complexes are going to be nested, one contained in the other. I'm going to have a finite number of changes. At each step, I compute the homology. That's the fingerprint. That's persistent homology, the persistent homology of my point cloud. All right, so let's start from this point cloud. It's very simple. I just have 6 points in R2. I'm giving you coordinates, so we have a notion of distance between them. In particular, I'm going to cancel what I'm writing now in a second. I have that the distance here is 1, 1, 1, 1, 1, and 2. Okay, and then I have, of course, square root of 2 and the sums. Okay? Okay. I want to construct the sequence of simplicial complexes following the heuristic iteration. Now, since the minimal distance between 2 points is 1, until time equal 1, nothing happens. Okay? So if t is less than 1, I have no one-dimensional simplexes. I have just vertices, so I have nothing. No. I'm writing no simplices. Okay, of course I have the vertices, but just let me write that. No simplices apart from the vertices. Time equal 1, then something finally happens, because I can join these two. I can join these two, these, and these. And nothing else, right? Because all the other pairwise distances are greater than 1. I might make mistakes, so please follow the computations with me, okay? I might get something wrong. Okay, now, the next closest distance would be between these 2 points, or these two, at time, and that's square root of 2. Okay, so until between time equal 1 and time less than square root of 2, nothing happens. I'm left with this shape here. Finally, at time equals square root of 2, I have a bunch of things to add. Let's start. Let's do it with order. I'm adding these two, this edge here. But I'm not only adding this edge, because now if I consider these 3 vertices, 1, 2, and 3, pairwise distances between them is all the pairwise distances are less than time, so I'm adding also these 2 simplex. Okay? Similarly, I'm adding these 2 simplex. Similarly, I'm adding this edge and the other 2 simplices. Okay? I'm not going to color them, you get the idea. Okay? Similarly, since all these 4 vertices have all the pairwise distances less than square root of 2, I'm also adding the 3 simplex defined by these 4 vertices. So I'm also adding the solid tetrahedron. Okay? So this is something that's solid, is filled in. There's no holes there. Okay? All right. Then, again, until t less than 2, nothing happens. At t equal 2, I have a bunch of things to add. Okay, I have this thing here. Oh, I should have added this as well before. And the corresponding simplex. Okay. So I have something that looks like a solid ball on this side here, plus a triangle, plus. At time equal 2, I'm adding this. I'm adding these and the corresponding 3 simplets defined by these three points, and possibly other things. Okay. The point is that from time equal 2, I have a unique blob with no holes. Okay. Am I adding this as well? What's it? No, this is not. Time equal 2, I have a unique blob. Okay. With no topological features. I have no one-dimensional holes and no two-dimensional holes. Okay? Okay, so that's schematically what's happening. Now, once I reach a state in which my set of points has become a single blob with no features, then nothing else can happen afterwards. Okay, so I can consider this stage here as a final stage. I reach the unified blob situations. Nothing is interesting anymore. All my data is a connected ball with no holes. Okay, so time equal 2 in this case is going to be our final set. So this is supposed to summarize all the information I gathered. I have that from t equals 0 to t less than 1, my set of points is a set of points, so I have b0 equal 6 and b1 equal 0. I'm not talking about b2 because I don't have it, okay, so I'm not going to write it. From t equal 1 to t less than square root of 2, I have b0 equal 2 and b1 equal 1. Then I have, in this new interval from square root of 2 to 2, I have still 2 connected components and now no first homology. And then finally, from t equal to infinity, forever, I have a single connected component, and no homology. This is 0. Homology is cancelled. Any question here?
Could you define the Betti number then, the third one, the B2, for the 2 last cases, since you have a solid tetraedron?
So I've been asked to mention what's the Betti number 2 in these 2 cases. That's 0 because, again, I have the solid thing. Let's forget about this last part, okay? This is just a unique thing with no holes. But this is apart from the fact that I have a separated point, even this space here is a unique blob with no holes because I have the solid tetrahedron between the 4 points. Okay, so I have no two-dimensional hole. If I only had, the 2-dimensional simplices forming the boundary of the tetrahedron, but nothing filled in, no 3-dimensional thing filled in, I would have had Betti number 2 equal to 1 because I would have had a sphere-like thing with a 2-dimensional hole. I don't, so Betti number is 0. Betti number 2 is 0.
Thank you.
Okay, we're almost done, okay? It's the last part of the computations. I just need... Yes.
Pretty much.
Yes.
I think if you keep increasing t, there's something else.
Say it again, sorry?
If you keep increasing t up to, let's see, square root of 10 or something, wouldn't you get another connection?
You would get definitely, you would get other connections, but you wouldn't get any feature, because you would get many connections. So, let's say, for example, at some point you are going to connect these, okay? But when you connect these, you're also going to put the triangle. So no homology is great question. Yes, yes. Of course, you are creating new connections, but no meaningful one, okay? Because for every new connection, you are going to fill in that connection by higher dimensional synthesis, okay? So really nothing is going to change anymore. We are going to see, the first example we are going to compute using the software in next week is going to be exactly this point cloud, so we can check that we did the right computations, and we can check, we'll see with the software that that's exactly what's happening. Thank you for your question. It was very nice question. I should have mentioned that. Thank you. All right. So I'm just copy and pasting this here to have it in front of us. I want to transform this information about how the Betti number changed when the time parameter increases in the filtration. I want to encode all this information as a picture, okay, using the so-called persistent barcode. And I'm doing that by drawing the following thing, okay. I want to consider each feature appearing in the filtration as a bar whose length is dependent on how long it stays, on its persistence. That's why we have the name persistent homology. Okay, how long a feature stays in the filtration. For example, I start by having 6 separate points, so I start by having the 6 zero-dimensional features, okay, 6 connected components. Let me draw them in this way. I start by drawing 6 points, okay? Now, these 6-dimensional features are born at time 0, then they all stay separate, until time 1. So at time 1, 5 of them are merged and only 1 is left. And only 2, are left. So which one was this one? All right. And they stay separate, these 2, until time equal 2. Okay, so let's say that time equal 2 is this. And from 2 on, I'm left with only 1. Okay? I'm sorry, I'm making a mess. Give me 1 second, and I'll try to draw a proper picture. So here, this is time equal 1, then another interesting point is time equals square root of 2, then time equal 2, and then infinity. So I'm starting with 6-dimensional features. They stay all alive until time 1. Then I'm left with 2 until time square root of time equal 2, and then I'm left finally eventually with 1. That's the barcode representing the 0-dimensional homology of my point cloud. For what concerns 1-dimensional homology, I have a unique feature that's appearing at time 1 and that's dying at time square root of 2. Okay. This is 1 homology. And this is 0 homology. Okay, so this is a schematic way to represent, not exactly what I draw, okay, to represent the how the features are born and die in the filtration. Okay. Similarly, I can encode, and this is called a persistent barcode. Okay. As everything I said, there's an algebraic way to define this object. Okay, and everything works fine, and everything is well defined, and you can do computations on it. This is just to give you an idea. Similarly, you can draw a so-called persistent diagram by interpreting each feature, each homology class appearing in the filtration as a dot in a plane, drawing a plane. This is the line y equal x. X-axis represents birth time. Y-axis represents death time, and I can represent all my features as dots. Let's start from H1, which is easier to draw. I have that my feature is born at time 1 and dies at time square root of 2. This is the dot. Then I have a bunch of zero-dimensional features, all coming to life at time 0 and dying, at time 1. So here there should be 4 of them. I'm just doing 1. And then I have one feature coming to life again at time 0 and dying at time 2, and then I have 1 which never dies. I draw that here. Okay. Now this is not the best example to have a nice persistent diagram. The barcode look much nicer. Anyways, let me just repeat. You can represent all the features as dot in a plane, having as coordinates birth time and death time in the filtration. Okay? Now, this thing here is a much better looking example of what a persistent diagram might look like. Okay? I just want to say another couple of quick things and then we'll call it a day for today. I just want to say that once that you are able to encode all the information about these topological features appearing and dying in the filtration starting from a point cloud, and once you can talk about persistent diagrams and you work with persistent diagrams, you can do things with them. First important thing you can do with them, if you have 2 different diagrams, D1 and D2, shown here as superimposed to each other, D1 being the blue and D2 being the green, you can define distances between them. And defining distances will give you a way to understand how similar two persistent diagrams are, and thus understand how similar in shape the 2 initial point clouds are. So if we are talking with real data, this will give us a way, for example, to cluster different point clouds, okay, by computing, pairwise distances. I don't want to go into the details. There are several different kind of similar but different distances you can define. They all kind of rely in finding the best possible way to match points in the diagrams and then compute some distance between matched points. For example, for I think P equal 1 and Q equal 2 or vice versa, this Wasserstein distance here is once you found the best possible matching, it's just the equivalent distance between the points. Okay? Again, we'll see this as an example in a week from now, and we'll compute using the software Irene the several Wasserstein distances between them, and we'll check that with this choice of PRQ or the other way around. We get the equivalent distance between the best matching, and the best matching is just the one that draws. Not important to have an idea of the definition of the distances, just know that we can compare diagrams, and thus we can meaningfully compare different point clouds from a shape/structure point of view.
Sorry, could you please repeat the difference between D1 and D2?
So these are two different diagrams. They're just drawn, superimposed to each other. Okay, that's like yes, just two different diagrams. We'll see that again in a week from now. This is just, an anticipation also to make things easier for Oliver, since he's going to go a little bit deeper in the technicalities and a little bit deeper in the kind of things you can do with persistent homology, variation on the basics, and this will be what we're talking about today. All right, last thing I want to do. All right, yes. Perhaps I don't have time to mention that, but we'll see in an example how powerful can be, how important can be to be able to compare using these distances and using persistent homologies different shapes. In particular, I'll show you that we can recognize point clouds that look like circles, and we can distinguish them, for example, from point clouds that look like two separate circles. Okay? Just by computing their persistent homology and by computing Wasserstein distance. Now, persistent diagrams are very nice because of that. One thing you can't do with persistent diagrams is sum them. So if you have, let's say, several different point clouds, and for each one of these point clouds you compute the persistent homology and you have the persistent diagram, you can't, for example, take the average, okay? Because there's no meaningful notion of a sum of two persistent diagrams. That's kind of a problem, because if you want to do statistics on data, you kind of want to, be able to sum and average things. Good news, there's a way to transform a persistent diagram in a new object called persistent landscape. This is going to be a sequence of functions, thus, speaking in technical terms, something, an object living in a Hilbert space, so something I can sum. So if I have two persistent diagrams, I cannot take their sum, but I can transform both into two sequences of functions called persistent landscapes, and once I have that, I can sum them. And the information contained in persistent landscape is exactly the same thing as the persistent diagram. Indeed, I can go back from a landscape to the persistent diagram. There is a one-to-one correspondence. Okay? I don't want to give the definition of how the persistent landscape is constructed from the diagram. I'll just show you very quickly. If you start from the persistent diagram, so something that looks like that, a set of dots representing your features, you can take the vertical and horizontal projections on the x equal y line of all the dots, like I'm doing. Okay? Then, as a first function in my sequence, I can take the function tracing the max points of these triangular landscapes I draw. This is going to be lambda 1. Then I can take lambda 2, the second maximum point. And I can take lambda 3, and so on. In this example, I have that lambda 1, lambda 2, and lambda 3 together are my persistent landscape. Sequence of functions, if I have two, I can sum, I can subtract, take the average. I'm done here. I just want, as promised, to spend 2 minutes in discussing these references. I want to suggest you. So if you want to know more about homology, simplicial homology, simplicial complexes, and all the algebra behind, homology, possibly the best textbook I can think of is Algebraic Topology by Alan Hatcher. And this is, I think, the best one because it contains everything. It is a little bit schematic, but there is everything there. So there is not much intuition, perhaps, but there is everything, and it's very clear, and it's in very simple terms. And most importantly, it's freely available. Okay, if you Google the title of the book and the author, or if you go to this website here, you can download it for free. Fun fact, this person, this Alan Hatcher, wrote, I don't know, but several algebraic topology books. They're all freely available from his webpage. So if you want to, continue the study of algebraic topology, not only stop at homology, you can do that just by reading all of these freely available books. If you want to know more about the computational aspects of algebraic topology, again, persistent homology and much more than that, possibly the best source would be Vidit Nanda's course. Vidit Nandas is a professor here in Oxford. It's the second or third year now that he's doing the computational algebraic topology course. He has lectures available on YouTube, freely available lecture notes, exercises, and whatever. So, it's an entire Oxford course. High level education. Vidit is great, and everything is freely available on it. And then something less, involved. There's this web page in the website towards data science that it's like a notebook, an HTML thing, interactive, that gives you a non-math introduction to PH with lots of examples and interactive plots. And I think it's a great source to have a naive idea of what's going on. All right. Tomorrow, Oliver is going to tell you something more about what you can do with persistent homology. In a week from now, we're going to basically see examples, implementations of the last part of today's talk. So we'll use software Irene in Julia. We'll start from point clouds. We'll compute persistent diagrams and barcodes. We'll interpret geometrically some of the most important topological features appearing. We'll compute distances, and we'll see what we can do with distances. I think we can finish here. Is there perhaps one last question? After that, I'm going to be super tired, so. All right. I don't see any other question. Feel free to send me an email if you have any afterwards. And as I mentioned at the beginning, we should be recording this. So hopefully, if you send an email to either myself, Oliver, our other lecturer, or Heather, our organizer, in a few days we should be able to point you to the recording if everything worked out fine. Thank you so much for coming. Looking forward to see you tomorrow. Bye-bye.
Thanks, Agnese. Thank you.
Thank you for coming.